derivatives and differential rules. Then we're gonna consider the partial derivatives, specifically the extension of the univariate derivative case to the multivariate cases. We're going to talk about Jacobian gradients with respect to matrices, and then we'll consider the biggest application of all these operators in machine learning, and specifically the backpropagation procedure, which is commonly used in order to train neural networks. So let's start with the derivative plots. So we'll consider univariate case where we have a function of one variable, and this variable is the scalar x. And for that function, the derivation of the function at point x0 is the following limit, if this exists. So we take a slight displacement from x0, and that displacement is recognized by this amount h, value h, and we take the difference between the function value at that displacement, which is f x0 plus h, minus f of x0, and we divide this on the size of that displacement h. And then we take the limit of this when h goes to 0. So if this limit exists, then we call that limit a derivative of the function, univariate function f, at the point x0. And and in this case, we call the function differentiable at the point x0. Also, if the function has derivative, and this derivative itself is a continuous function, then such functions are called smooth functions. And typically, in many applications in machine learning, we'll be dealing with the smooth functions, and mathematicians, they like smooth functions because, yeah, a lot of properties of these functions can be established, because they allow this differentiality for the first derivative, and then you can study the property of this derivative because of its continuous nature. Now, let's speak about the geometric interpretation. So what's that, this limit? So now in order to do that, let's consider some univariate function. So that's why on this xy plane, we consider the function f of x. And this function of x, let's assume that we want to compute the derivative at the point x0. And at point x0, it has the value f of x0. So as I said, what we do, we consider the slight displacement, so x0 plus h, and we compute the corresponding function value at that displacement, so f of x0 plus h. And then the difference between f of x0 plus h minus f of x0 will be the length of this side in this right triangle. And then the h, the displacement value, will be nothing but the difference between x0 plus h and x0 point, which will be this side in this green right triangle. So therefore, if you recall the trigonometry course in this school, you know that in the right triangle, the ratio between this side and this side, it's called the tangent of this angle gamma. So therefore, basically, this ratio is nothing but this tangent of this slope vector gamma. And therefore, when we'll take the transition as h goes to infinity, this right triangle will be transformed just to one point. It will become infinitesimally small and will be converted just to one point. And therefore, this ratio will be the tangents of the tangent line to this function of f(x) at the point x0. That tangents of this tangent line is also called slope, or it's also called the slope of the tangent line and the point x0. So that's the geometrical interpretation of the derivative of the univariate function. But please keep in notice that not all the functions are differentiable. So for example, if we consider the function which is the absolute value function, and we consider the point x0, which is equal to 0, then at that point, which is green here, it's impossible to compute that limit. So this limit does not exist there. So therefore, this function f of x, which is equal to the absolute value of x, is non-differentiable at the point x0. And in machine learning, because of that, actually, there are different tricks that people have to do in order to work with that. And the reason why this function pops up in machine learning is when we consider, for example, L1 norm, and L1 norm is actually sum of the absolute values. And then, like, if we use the L1 norm as a regularization term for our loss function during, let's say, the training, now we cannot just apply the gradient computation, because strictly formally speaking, that function becomes non-differentiable everywhere, and that's why it's problematic. And there are tricks that people use, and there's also the extension of the notion of the gradient, which is called subgradients, in order to cover these cases. But this is more developed thing. So now, let's discuss how actually we compute the derivatives, right? So typically in the calculus courses, we know that there's basically a table of derivative of the very popular functions, and typically this table looks like something like that. So where you have a range of all different functions that you typically have to like deal in different fields, and in machine learning specifically, like this table covers basically all the functions that you have to deal in machine learning, and it actually represents different forms of the derivatives. As you can see, all these functions are smooth because all these derivatives are continuous functions themselves. Let's consider some example how we got this stable values. So, for example, we'll consider this quadratic function x squared. So, following the definition of the derivative, in order to compute the derivative of the function x squared, yes, at any point x, what we do, we consider the limit x plus h squared minus x squared divided by h. Yes. So then when we rewrite this ratio in the denominator, you will see that x squared and x squared, they cancel out each other, and therefore the only expression which will be left in the numerator part will be 2hx plus h squared. And then we divide by h, which is the size of the displacement, and we got, as a result of that ratio, we got 2x plus h. That will be the ratio, that will be the result of the ratio. And then we need to try to find the limit of that when h goes to 0, and it's very easy to do, because in this case it will just be 2x, because the h part, the additive h part, will just vanish. So therefore, basically, we're proving that the derivative of quadratic function x squared at any point x is nothing but 2 multiply x. So, and in the similar way, we can basically show every value, every derivative result in that table. It can be basically established by carefully considering the limit of this ratio, the difference between function value at the displacement and at the point at which you want to compute the derivative, to the size of the displacement. Now, another important thing that we need to definitely cover is, okay, assume that we establish these known derivatives for this set of functions. But what if I have something more sophisticated, like some functions which are more complex? And typically these more complex functions, they kind of like build it as a basically building from these building blocks, and the building blocks are these more like simple functions which were presented previously. So typically what we do, we take these simple functions and then we construct something more sophisticated from that. And then the question, okay, if that's the case, how we can compute the derivative of this more sophisticated thing? And in order to address that, we typically in mathematics, we apply the rules of differentiation, and there are several of them. We'll start with the the derivative of the product. So assume that we have two functions, f of x and g of x, and both of them are differentiable at point x. And now we want to compute the derivative of the product of these two functions at the point x. And that's what the product rule establishes, and it tells the derivative of the product of these two functions is equal to the derivative of the first function multiplying the second function plus derivative of the second function multiplying the first function. So let's consider a quick example. Assume we have two functions, f of x is equal to x squared and g of x is equal to cosine of x. And we want to compute the derivative of the product of these two functions, which will be x squared cosine x, at some point x. So following this product rule, how we do that? We firstly compute the derivative of the x squared at this point x, multiply on the second function, which is cosine x, plus we compute the derivative of the second function, g of x, which will be cosine x, derivative of the cosine x, multiply on the first function, x squared. Then coming back to our table values, using that cosine x derivative, it's minus sine of x, and the derivative of the x squared is 2x. We eventually arrive to the result for the derivative of the product of the function, which will be 2x cosine x minus x squared sine x. And this is how we basically using this table of the known derivatives, how we can actually compute the derivative of more sophisticated function, which is formed as a product of these more simple functions. Now, the second rule that's also used in order to compute the derivatives of the ratio to two functions, it's called quotient rule. So assume that we have again two functions of x and g of x, that they're differentiable at the point x, and then we want to compute the derivative of the ratio of these two functions, f of x and g of x, and typically we assume that here the point x at which we want to compute that derivative, it's not the point where g of x converges to 0. So then the quotient rule tells that in order to compute that derivative, the result of that derivative of the ratio is the following fraction, where in the denominator you have the derivative of the denominator f of x multiply on the numerator function g of x minus the numerator function f of x multiply the derivative of the denominator function g prime of x, derivative of the g of x, and divided by the square of the denominator function g square of x. So let's consider the example. Assume that our numerator function f of x is x squared, and our denominator function g of x is cosine of x. Then we want to compute the derivative of this ratio, x squared to cosine of x. Following the quotient rule, we firstly compute the derivative of the numerator, which is x squared, and we know that it's 2x, and we multiply that on the denominator function cosine of x, so that's why we have 2x cosine of x. Then minus the denominator function, x squared, we don't touch it here anymore, and then multiply that x squared on the derivative of the denominator function cosine of x, and we know that that will be plus x squared sine of x, because we know that derivative of the cosine of x is minus sine of x. That's why we see the change of sign here. And then we take that ratio to the square of the denominator function, which is cosine of x. That's why we have a cosine square of x. And this is how we compute the derivative of the ratio of the two functions, f of x and g of x. Again, you can see that now, if we know this derivative of the simple functions, we can easily compute the derivative of a more sophisticated function that is constructed as a ratio of these non-functions, simple functions. The third rule that we're going to cover here, it's called sum rule. And in sum rule, you have, again, two functions, have a g of x, and they are differentiable. And also you have two scalars, any scalars, alpha and beta. They are just the numbers. They don't depend on x. And then we want to compute the derivative of that linear combination, alpha multiplier of f of x plus beta multiplier of g of x. And the sum rule tells that the derivative of that will be nothing but alpha multiplied the derivative of f of x plus beta multiplied the derivative of g of x. Based on that result, you can actually see that the differential rule or differential operator is linear, because when you apply it to this linear combination, is nothing but the linear combination of the results of the operator applied to each of the components. So that's why in math we also say that differentiation is a linear operation. So let's again consider some example how we do that. So again, consider this function f of x, which is x squared, and g of x, which is cosine of x, and assume that we want to compute the derivative of this linear combination of these two functions, 4x squared minus 2 cosine x. In this case, alpha is equal to 4, and beta is equal to minus 2. And again, following this sum rule, what we got is we get 4 multiplied on the derivative of the first function, which is derivative of the x squared, and we know that the derivative of the x squared is nothing but 2x. And when we multiply 4 on 2x, we got 8x. That's why we have 8x here. Now minus 2, because beta now is minus 2, multiply on the derivative of the second function, is g of x. And again, we know the derivative of the cosine of x, it's minus sine of x. So therefore, when you multiply minus 2 on the minus sine of x, you got plus 2 sine of x. So that's why this is how we compute the derivative of the linear combination of two functions. Now, the last important operation here that we're going to cover, it's called chain rule. And this is a very important operation in both in math and specifically in machine learning, because this is operation that allows us to compute the derivative of the parameters of the neural network, because neural network represent the stack of the layers, and the output of the previous layer goes as an argument as an input to the next layer. So therefore, you basically have this nested structure. And then in order to compute the derivative of the nested structure, what we can use is called chain rule. So in the chain rule, what we have two functions, f of x and g of x. And then g of x is used as an input to the function f of x. So that's why we write f of g of x. So typically in math, we call these functions compositional functions or complex functions or compositional functions. Sometimes we also describe these situations as nested functions. So if we have a sequence of functions such that each of them it's an argument of the like one of them will be argument of another one, we basically describe it as a nested structure. And this is what we typically have in neural networks. So the chain rule, computation of the chain rule derivatives is simple. It basically tells that if you want to compute the derivative of this complex compositional function, f of g of x, then you need to compute the derivative of the outer function, which is f of x, evaluate that at the g of x, and then you multiply that on the derivative of the inner function, which is g of x. So, okay, let's consider that on this example. So we have function f of x, and in this case, f of x will be cosine of x. So that's why in order to distinguish x and the argument, which will be x squared, I denote that we consider the outer function f of z as a function of z, and that's a cosine of z. That's the outer function. And the inner function g of x is nothing but just a quadratic function x squared. So in this case, if you consider f of g of x, it will be exactly cosine of x squared. So now if we want to compute the derivative of the cosine of x squared, we're following the chain rule, and we see that it's a derivative of the outer function, which is a cosine of z. And we know that the derivative of the outer function, cosine of z, it's a minus sine of z. But now, instead of z here, we need to use this inner function following the chain rule. Before we got this minus sinus x squared, because instead of z for the outer derivative, we use g of x, which is x squared. That's why we got the minus sinus x squared. And then we need to multiply that on the derivative of the inner function, and the inner function is g of x, which is x squared, and the derivative of the inner function is nothing but 2x. So therefore, when we compute this derivative, we got minus sine of x squared multiplied 2x, and this is minus 2x sine x squared, and this is the derivative of this compositional function. And now again, if you have like what we have typically in neural network case, we have this nested compositional structure, but each of the component in that structure is basically formulated in terms of these simple functions. Now, following these rules, you are capable to compute the derivative of every sophisticated function, because you can break it down to the computation of the derivatives of these simple functions that you already know, that you can use from the results for which you can use from this table. Now, please keep in mind that everything that we discussed before was for the case of so-called univariate function, when you have x, which is the one-dimensional value, which is the Chitrin number, and your function f take this x and output some another real number. So that's a univariate function. But the case that we're going to consider more, and we'll have to spend more time, and this is actually a more general case, is so-called multivariate function. So multivariate function, it takes the input not just the x one-dimensional, but it takes the input a vector, so n-dimensional vector, and it outputs a real number. So that's why we write that we have f, that x from n-dimensional Euclidean space, so it takes input, it eats n-dimensional vectors, and it outputs numbers. And now we want to extend the notion of the derivative, but for the multivariate case. And how can we do it? Well, in order to do that, in math, we introduce so-called partial derivative case. So we consider a point x, which will be a vector, which has component x01, x02, up to x0n. And we want to compute the partial derivative of the function f of x, multivariate function of f at that point x0. And in order to compute that, following the univariate case, for each of the component, we have n components, we consider the limit of the displacement at the corresponding component with respect to which you want to compute the partial derivative of the function from the evaluated at this displacement h1. So, for example, we consider let's consider this the first computation. So we compute the partial derivative of the function f with respect to the first component at the point x0. So what we do, we basically fix all the other components except the first component. So we fix x02, x03 up to x0n. But what we do, we slightly change the first component. We write x01 plus h1. So this h1 is this displacement for the first component. And we compute the function at that point. And then we compute the difference of the function at that point, where we basically only do slight displacement with respect to the first component, minus the function of the value at the point x0, and we divide that on the size of that displacement, h1. You can see that this is very similar to the univariate case, apart from the fact that now we have to deal with the fact that we have other components as well. And the way we deal that, we just freeze them. We said, okay, when we compute the partial derivative with respect to the first component, we will freeze all other components and freeze to the values of the point at which we want to compute the partial derivative. And only in this case, we'll consider our function will be just a function of the first component, univariate function of the first component. And then we can apply this already familiar notion of the limit in order to compute the partial derivative. Now, the same trick we do for the second partial derivative. In order to compute the second partial derivative, or the partial derivative with respect to second component, at the point x0, what you do, you freeze all the other components apart from the second component. So you freeze x01, you freeze x03, x04, up to x0n, but not x02. And at x02, you actually consider this displacement. You add this plus h2, and then you consider the value of the function at this displacement point minus the value of the function at the point at which you want to compute the partial derivative, and divide it on the size of that displacement, on the size of h2. And you take the limit. And you basically follow the same strategy for all the n components. So like the difference between univariate function and multivariate function when it comes to derivative is that for univariate function, the derivative will be just 1 at any point if this limit exists. But for the multivariate function, the notion of the derivative will be relying on the collection of partial derivatives. And because you have n different components, the number of these partial derivatives will be also n. But each of these partial derivatives, again, it's computed as if you freeze all the other components that are not relevant for you for the computation of the specific partial derivative to some value. And then when you do that, the result will be just a function of one variable, which will be the variable that corresponds to the component at which you want to compute the partial derivative. And then you follow the standard limit definition of computing the derivative of that univariate function. And as a result, you got the partial derivative of the multivariate function. So now let's illustrate that with some quick example. Assume you have a function of 3 variables, x1, x2, x3. So it takes this 3-dimensional vector. And as a result, it outputs this expression. So it takes the first component, take it as square of the first component, then it takes add it to the product of the first and the second component, x1, x2, and then finally take the cube of the third component divided by the second component, and again add it to the result. So this is just an example of the multivariate function of acting in 3-dimensional Euclidean space. And assume I want to compute the partial derivatives of that function at the point 1, 3, 5. So when the x1 is equal to 5, x2 is equal to 3, and x3 is equal to 5. So let's take this notion of this partial derivative and let's follow the definition. So again, in order to compute the partial derivative of that function f of x1, x2, x3, and with respect to x1, you treat all other components apart from x1 as just constant. And then you consider that function as only the function of x1. So when you take that approach, when you take that derivative, you will see that, okay, then when you take the derivative of that function with respect to x1, the derivative of x1 squared will be just 2x1. Then the derivative of x1 multiplied x2 will be just x2 because you treat x2 as a constant. And therefore, like it following this linear property of the differential operator, the derivative of with respect to x1 of this product x1 multiplied x2 will be nothing but x2. Therefore, the derivative with respect to x1 of this x3 cubed divided by x2 is 0 because this will be a constant with respect to x1 because this ratio does not depend on x1. So you treat that as a constant, so therefore like the derivative with respect to x1 will be 0. Therefore, the derivative of this function with respect to x1 will be nothing but 2x1 plus x2. And because you want to compute it at the point 1, 3, 5, right? Then what you do, you take 2x01, which is 1, so you take 2 multiplied 1, plus x02, which is 3, plus 3, and that gives you 5. So that will be the value of the partial derivative of this function, x1 squared plus x1 multiplied x2 plus x3 cubed divided by x2 at the point 1, 3, 5. Okay, now please notice that because of this specific form, in order to compute this partial derivative, we don't need, we never use x3 value because this partial derivative turns out that it does not depend at x3 at all. Now, let's compute the partial derivative of the same function, but with respect to the second component. Again, we're gonna treat all other components, which are x1 and x3 as a constants, and only variable that we'll consider here in order to compute that partial derivative will be the second component x2. Okay, so in that case, when we take the derivative of the x1 square with respect to x2, because we treat x1 square as a constant, in this case, it will be 0, so it will vanish. Now, when you compute the partial derivative of the x1, x2 with respect to x2, because x1 is a constant, it will be nothing but x1. Again, following this linear property of the differentiation operator. And then please notice when we take the derivative of the third part, of the third additive term here, x3 cubed divided by x2, we treat x3 cubed as a constant because we take the derivative of the with respect to the second component, so that's why we'll have x3 cubed untouched. But we'll have to take the derivative of the function 1 divided by x squared, but 1 divided by x2, and then following this quotient rule, like the derivative of the ratio, you can find that it's nothing but minus 1 divided by x2 squared. So therefore, the partial derivative of the function of x with respect to x2 will be nothing but x1 minus x3 cubed divided by x2 squared. And now you can see that if you want to compute that partial derivative at this point 135, you will need all the values here. You will need x1, and that's 1. You will need x2, because x2 is in the denominator of that fraction part here. And you will need x3 value, which is 5. And the result will be minus 116 divided by 9. And that's the value of the second partial derivative, with respect to the second component. Finally, we need to compute the partial derivative with respect to the third component. And again, we treat all the other component, which is x1, x2 as a constant in that function. And the only variable that we'll recognize here will be just x3. And in this case, when we take that, we see that both these first two terms, they don't depend on x3. That's why the derivative with respect to 1 will be nothing but 0. And the only term that has x3, the third component, is this last term here, which is x3 cubed divided by x2. But keep in mind that x2 now, although it's in the denominator, but it's recognized as a constant. So that's why it will go untouched. And therefore, we'll need to only just to take the derivative of this x3 cubed, which will be 3 multiply x3 squared. So it will be 3 multiplied the square of the third component. And again, now if we want to compute that at the point 135, the only components that will be important here will be x2, which is 3, and x3, which is 5. And the result will be 25. So therefore, now we computed all the three partial derivatives of this function, x1 squared, x1 plus x1, x2 plus x3 cubed divided by x2 at the point 135. Now, let's talk about what's the geometrical interpretation? What does it mean? Because keep in mind that when we consider the univariate case, we describe what's the geometrical interpretation. It's a tangent of the tangent line that touches this function f, univariate function f, at the point x0. And this was the geometrical interpretation of the derivative of the function. Well, the similar geometrical interpretation can be described for the multivariate function. So consider the multivariate function, which is z is equal to f of x and y. Z is equal to f of x and y. And in this case, if we want to compute the partial derivative at the point x0, y0, so what do? We actually, following this idea that when we want to compute the partial derivative with respect to one of the components, we freeze all the other components as a constant, and then we basically will reduce the formula as just a formula of computing the derivative of the corresponding univariate function. So this is a similar case here. So for example, if you want to compute the partial derivative with respect to the first component, which is x, at the point x0, y0, what you do, you construct the function, which is the function only of the only on the first component x by freezing the second component to be equal to y0. So you consider a function of f of x, y0, and that function will be univariate function. And then you basically can apply the same geometry when you compute the gradient of that univariate function with respect to x0. Yeah, it will be nothing but the tangents of the slope, or slope of the tangent line, to that univariate function constructed at the point x0, y0, and that will be nothing but the geometrical interpretation of the first partial derivative, or the partial derivative with respect to first component x. And the similar with respect to second partial derivative. So in this case, we fix x0 and we consider the function, univariate function, or that has form f of x0, y, and that will be just a function of y. And then when we compute the partial derivative, again, it will be the slope of the tangent line to that univariate partial derivative, to that univariate function f of x, y, f of x0, y, to that at that point x0, y0. So in other words, the partial derivatives are nothing but the slope of the tangent lines as at the restriction of the original function to the restriction with respect to with respect to the components at which you want to compute the partial derivative, and the partial derivative will be nothing but the slope of this tangent line to these restriction functions. Now, when we equipped with the notion of the partial derivatives, we are ready to introduce the notion of the gradient, and the gradient is analog of a derivative, but for the multivariate function. So keep in mind that we started when we started to discuss the extension of the derivative of the function to the multivariate case. We wanted to say, okay, what is that analog but for the multivariate function? So, and that's analog is gradient. It's also called the derivative of the multivariate function. And the derivative of or gradient of the multivariate function is nothing but a collection of its partial derivatives. So this gradient, now keep in mind, now it's not a number as we had in the multivariate case, but it's actually a vector. And the size of the vector is equal to the size of the domain of the function. So if your function takes the input from the n-dimensional Euclidean space, the gradient will be also n-dimensional. And the reason is why, because it combines all the partial derivatives of that function, and the number of the partial derivative is equal to the number of components in the input vector x. So if we have n-dimensional vector, yes, it has n components, and with respect to each of the components, we compute the partial derivative, and therefore the gradient also will be n-dimensional object, so it will be n-dimensional vector. Now let's see the example of the gradient. Again, we consider the previous function for which we computed the partial derivatives. It was function f of x1, x2, x3, which is x1 squared plus x1, x2 plus x3 cubed divided by x2. And at the point of x0, which is 1, 3, 5, we already computed all of its partial derivatives. Partial derivative with respect to x1 at the point x0, partial derivative with respect to x2 at the point x0, and the partial derivative with respect to x3 at the point x0. And they were 5 minus 116 divided by 9 and 25. So we combine them, and we can represent them as a three-dimensional vector, and this is a gradient of the function at this point. So now if we're talking about the geometrical interpretation of what's that in the gradient. So the gradient now can be recognized, so if we consider this paraboloid case, which is the two-dimensional, it's a second order surface in three-dimensional space, which is x squared plus y squared, then we can compute the derivative, the partial derivative with respect to each of the component. Here it will be x1 and x2. These two, because it's a second, because it's a two-dimensional case. Yes, it's z is a function of x squared plus y squared. So the z function will act on two-dimensional Euclidean space. So it will take two-dimensional vector, and the output the value. therefore the gradient will be also two-dimensional vector. And the gradient vectors are note that the gradient vectors are calculated in the component form, but are translated to their respective input points on the xy plane in order to show better the direction that is associated with these points. But now when we fold the whole space, xy, two-dimensional space, fold it to this surface, to this paraboloid, then this two-dimensional gradient vector that was depicted at the xy plane, now they will be transported to the tangent vectors at the surface. So here we see how they will be translated. So that will be the gradient of the function of z, which is f of xy at the point x1 and y1, and this will be at the point x2 and y2. And the geometric interpretation is that the gradient shows the direction of the steepest increase of the function. So if you basically imagine yourself standing at that paraboloid at this point, and you want to understand, okay, in which direction I should go in order to experience the highest increase of the function, the highest increase of the function, the fastest increase of the function. And this direction is defined by the gradient of the function. And therefore, the negative of the gradient is the direction of the fastest decline of the function. So this, and this is important observation that will be used when we'll discuss the optimization methods, and specifically gradient descent optimization method, when you follow the minus of the gradient in order to optimize your function. Because you want to make your function as small as possible, therefore you need to follow the direction in which the function experiences the fastest decline. And that is defined by the negative of the gradient. And just the gradient shows the fastest increase of the function. Now, okay, we described that for just the calculus part. Now, let's discuss a bit the machine learning application of this thing. And the specific application in which you will see well, first of all, the gradients, of course, they are heavily used in whole machine learning. So like typically as engineers, we don't see that because we have these software tools that has these auto-diff functions that can actually just by one simple call can automatically calculate you the gradient. Yeah, and it's very convenient. But we also need to understand, like on very simple example, why do we need to compute them, and what's the meaning of them, and how do we apply them in machine learning specifically. So here we'll consider the very basic task, which is linear regression task, which is assume that you have a collection of data points, x, y, and for each of them you have associated scalar value y. So like in this case, although it's I depict that as a two-dimensional, please keep that each of these x1, x2, x3 are actually are vectors living in some d-dimensional Euclidean space. So just like depict this d-dimensional Euclidean space as just one line here. And then for each of them, you have the value, scalar value, yi. And then you want to say, okay, I want to find the best linear approximator of that function, of the function of univariate function that maps xy to yi. And this linear function is basically depicted by this scalar code, omega w transpose x. The w is the weights that you want to find. So in this plot, you see this line. That's basically this w transpose x for different w's. And you want to find that line that fits this set of points in the best possible way. So what does it mean, the best possible way? It means that it minimizes the loss function. And the loss function is presented here. And if you look carefully at the loss function, you'll see that this loss function basically measures the error that this linear approximator, omega transpose x, experienced at every point x, y, yi. So omega transpose xi is the value of the linear approximation, and yi is the true value. And when you take the omega transpose xy minus yi squared, That's basically a penalty that you have to experience if you do not match, if your linear optimizer does not match yi perfectly. If it matches perfectly, then omega transpose xr minus yy is equal to 0, and you will not have any, and you will not experience and will not suffer from any penalties. But if omega transpose xy is not equal to yi, then that's basically error. That's the punishment that you have, the penalty that you have to suffer. And typically we consider the square of that. So because we want that penalties to be accumulated, that's why we cannot just take a scalar of that. Like it will not be informative between because of the different signs. Although you experience the penalty, but if you will not take absolute values of the square, these penalties can cancel out each other, and it will look like you have something like that perfectly fits your data, but actually everywhere it will make a mistake. In order to avoid that, what we typically consider is we either take the absolute value of the penalty or they take a square of the penalty. So here we consider the second version where we take for each point xi, we consider the square of the penalty of mismatch between our what our linear model predicts, which is omega transpose xi, and the true value yi. And then we want to, in order to find the best perfect fit, the best linear optimizer, the best linear model that fits that data, we want to find that omega star that minimizes this loss. So here, this omega star that minimizes this loss is basically this red line here, omega star transpose multiple on x. And that's what we want to find. We want to find this omega star if we have this data set, xi and yi. Okay, let's actually compute that. Okay, we know that from the previous discussion, we know that the gradient, the gradient direction shows the fastest increase of the function, and the negative gradient shows the fastest decrease of the function. Now think about that. If we want to minimize some function, which is minimize the loss functions here, right? We want to find the point at which the gradient vanishes. Why? Vanishes, it means it becomes equal to 0. Why? Because if the gradient does not vanish, if it's not equal to 0, then we know for sure that if we will follow the negative direction of that gradient, we will decrease the function. So we always will be able to decrease the function if we just follow the negative of the gradient. But at the point where the gradient vanishes, it becomes 0. That's it. We cannot decline that function anymore. So it's already reached like some sort of optimality, some sort of the minimum. And we know that if the functions are convex, or like the convex functions are functions that behave in a specific way, the vanishing gradient, the gradient is equal to 0, implies that we actually find the global minimizer. The global minimizer, so you cannot do better than that. That's really the point where the function takes the minimum value. Unfortunately for us, this quadratic loss that we have here for this linear regression task is a convex function. So therefore, the only thing that we need to find is the point at which the gradient is equal to 0. Because as I said, if it's equal to 0, then we know that we cannot make it even smaller by following the gradient descent. We just can't. And the convexity implies that there's no any other point that have this property, that the gradient is equal to 0. Of course, the situation is completely different when we discuss non-convex functions. And in non-convex functions, just to see that, oh, I found a point that where the gradient is equal to 0, does not imply that you have a point of minimality or optimality. You cannot even say that you have a local minimum. The only thing that you can see is just, at this point, the gradient vanishes, and that's it. And the example for that, if you consider, for example, a function which is a univariate function, y is equal to x cubed, right? And you consider the derivative of the function at the point x is equal to 0, you'll see that the function, at this point, the derivative, which is the gradient, but for your univariate case, also will be equal to 0, so it vanishes. But it does not mean that the function in any way is minimized at that point, because you know that if you just go slightly left from x0 to the negative, direction. So let's say compute -1, take a point -1. Then the function value will decrease. It will be -1 instead of 0 at the station point. So for the non-convex scenarios, just the fact that you find a point where the function, where the gradient of the function vanishes, does not imply that you find a minimizer. But the situation with the non-convex function is so difficult that that's basically the best we can hope for. And all these optimizers that in these libraries are implemented for optimizing these sophisticated machine learning models such as deep neural networks, transformers, CNNs, and so on. They basically only find the stationary points at which the gradient of the training loss vanishes. But basically, that's it. And we cannot do better than that because finding the local, or I'm not talking even about global optimizer for the non-convex function is an extremely hard problem. And we don't have any provable tools that can guarantee that you find this in any efficient way. So that's why, we sort of restrict it when we deal with the non-convex functions. Fortunately for us, in this specific example, as I said, this training loss that presented here is a convex function, and therefore it's this condition where the gradient is equal to 0. It's a sufficient condition for the global minimizer. So therefore we can actually claim that if we find a point where the gradient vanishes, such W star says that the gradient of the W star is equal to 0 vector, then we can surely say that we cannot do better than that. So that's the point at which we absolutely minimize this training loss. Therefore, we find the linear approximated linear regression model that fits this data as best as possible. Of course, with respect to this training loss that is formulated here. Okay, if that's the case, then let us focus on the point, how this point looks like at which the gradient vanishes or it becomes equal to 0. Well, in order to answer that question, we need to find how the gradient does look at this specific for this specific loss function. So let's do that. So we know that by the definition, the gradient of the loss function is the collection of the partial derivative of this loss function with respect to each of the component. So you have this the gradient with respect to the gradient of the loss function with respect to the first component, second component, and so on. Okay, let us fix some of the component. Let's say if we fix jth component, and let us try to calculate the partial derivative of this loss function with respect to that jth component. Okay, so in order to do that, we need to find the partial derivative of the jth component of this loss function here, which is nothing but our training loss. And then using the sum rule, we know that the partial derivative of the sum is the sum of the partial derivatives. So therefore, we can actually put this partial differentiation inside of the sign. So that's why we write it's a sum of all the data points. And then we take a partial derivative of this function with respect to omega j, wj, which is j's component of the parameter. Okay, now you can use the chain rule, so you can see that, okay, I can actually, in order to compute this partial derivative, I can actually compute the partial derivative of the just a quadratic function that takes as input this omega transpose xi minus yi. So in order to do that, following the chain rule, when you take the partial derivative of the quadratic function, is nothing that to multiply on the argument of the function, and the argument will be omega transpose xi minus yi. But then you need to multiply that on the partial derivative of the inner function, which will be this omega transpose xi minus yi. But please keep in mind that yi is just a scalar output. It does not depend on omega j, on this wj. So therefore, the partial derivative of the w transpose xi minus yi is nothing but the partial derivative of the w transpose xi with respect to wj. Nothing else. So that's why we can completely ignore yi, because this is a constant. Okay, cool. Now rewriting this. Now let's see what does it mean, this partial derivative of this scalar product. Well, in order to do that, we need to recall What is the scalar product? Well, the scalar product between vector W and vector xi is basically sum of the product of the corresponding components of these two vectors, right? So we have W1 multiply xi1 plus W2 multiply xi2 and so on plus Wn multiply xin. But we need to take that the partial derivative of this sum with respect to only omega j, only with respect to jth component of that. And the only term in that sum, in that scalar product, that will depend on the omega j will be omega j multiplied with the jth component of xi. So exactly this term here. Because all the other terms, they will not depend on the wj. And therefore we can ignore them. And when we take the partial derivative of this term with respect to wj, we'll just get xij. That's why we have xij. So we'll have just a jth component of the ith data point of the which is vector xi. Hence, when we'll repeat the same procedure, but for all of the components here, W1, W2, up to Wn, then you will get that your gradient with respect to W of the training course will be nothing but here. So keep in mind that this part will be common for all of them, partial derivatives, but what will change is this xi. Because for the jth component, we know that here it should be xij. So that's why when you write it in a vector form, it will be this vector. And keep in mind, this is vector because xi is a vector, and omega transpose xi minus yi is just a scalar multiplying that vector. Okay, so then fine, then we can actually write it in the following way. We just can multiply this xi on each of these terms, on each of the scalars here, write it in this way. And now we can, because omega transpose xi is just a scalar, we can multiply vector on the scalar either from the left or from the right. It doesn't change anything, because in both cases, right, it will be just a multiplication of each component of that vector on that scalar. So therefore we can multiply it from the left or right. Therefore here we change the order. First we write xi, and then we write this scalar omega transpose xi, because it doesn't change anything. And when it comes to the second component, please note that yi is just a scalar, so it's just sum of the yi multiplying the xi, and xi is the data points of vector. So here we don't even change the order. We only change the order in this for the first term here. But now what we're going to use, we're going to change the order inside of the inner product. So keep in mind that here we have omega transpose xi, but here we already write it as xi transpose omega. And we can do that because we know that the inner product or scalar product is symmetric, which is A transpose B is the same as B transpose A. It's the same thing, and you can actually easily establish that by considering what's the scalar product is. It's just a sum of the product of the corresponding components. Therefore, it doesn't matter. You write it as A transpose B or B transpose A. Okay, and when you do that, now you can regroup it back. So remember how we grouped the terms here in the previous. Now we can actually regroup it. We can regroup it again, and we can break down this inner product, and we can firstly compute xi transpose, and that will be a matrix, and then multiply this W. And this will be equivalent form of writing this previous expression. So in other words, what we'll get as a gradient of your loss function with respect to vector W is this expression here. The reason why we want to break it, because we want to separate this parameter vector W for which we want to compute from this data point information. So that's why we break it. So now you can see that you have the term that aggregates all the data points in the matrix, and this term you multiply on this W that you want to compute. And of course, we have this second part which we didn't do any manipulation with them. It's just a linear combination of these input data points scaled by the corresponding output values. Now, in order to write it in the compact and more beautiful, convenient matrix vector form, let us introduce these two objects here. Let us introduce the data matrix which basically combines all the X input data points, X1, X2 up to Xn, right? And we write them row-wise. So the first data point, X1 transpose, will be just a row, the first row of that matrix as the X data. The second data point, X2, will be just the second row of this X data matrix and so on. So it's a matrix that has capital N rows because you have capital N input data points. And also we aggregate all the output Y values, Y1, Y2, Y capital N, in one vector, and it will be capital N dimensional vector. So let's actually introduce these two objects, and then you can rewrite xi transpose, which this you have here. It can be conveniently written in a more beautiful and complex way as xt data multiply xt data. So you take this xt x data, like the data matrix, you transpose it and you multiply it on itself, and that's nothing but this sum of the xi transpose here. Keep in mind that this is a matrices, that's not a scalar. So yeah, like also what you can write that this second term, which is sum of the yi multiplied on xi, can be written in terms of these two objects that we introduce. Conveniently can be written as x data transpose multiplied on y data. And this is a good exercise. Just sit down and do it. Like I can give you a hint how to do it. You just, for example, if you want to prove this expression here, just try to calculate what will be, let's say, AB component of this matrix and AB component of that matrix for any A and B. Like let's say fix some A, fix some B, and say, okay, let me compute AB component of that, and let me compute AB component of that. And if these two are the same, then you know that matrices are the same, because two matrices are equal to each other if they equal component-wise. If AB component of one matrix is equal to AB component of the another matrix. And this is, if you do that more very carefully, this analysis, you will show that actually they are the same, so therefore this equality holds, and exactly the same way you can prove that this equality holds. Therefore, these two equations are correct. But given that result, now we can rewrite our expression of the gradient in this vector form, more convenient vector form, right? And therefore, if we want to find the point W star at which the gradient vanishes, we want to make this expression be equal to 0, right? And that basically gives us this system of linear equations, which I think is also called normal equation. So here, we basically showed you guys how you arrive to this normal equation in the linear regression from the point of, from the angle of the gradients. So basically the normal equation is nothing but the condition at which the training loss for linear regression vanishes or optimized. So the gradient of that training loss is equal to 0. And this is how you arrive to the normal equation. And this is how we compute the gradient. Okay, I think that's, I would like to stop here. Please everyone like and subscribe. Please try your attempts on solving this equation. And if you have any questions, ask your questions in the comment, and we will be glad to provide the more detailed explanation. I hope you guys liked it. And yeah, next time we're going to continue. We're going to consider the Hessian and the application of the Hessians. Yeah. Hopefully you like it. And everyone, please share your comments, share your feedback, and we will be glad to answer your questions. Take care. Bye bye.